זה גם בפורמט.
גם היעד לא כזה, לא, כן.
זה סרט של 5 שעות.
תקציב.
זה לא יותר. Okay. So today we speak about the thick thin decomposition. Maybe I'll get a better shot. So actually we will not completely need it for the proof, the main results, because intuitively the proof should go through the thick thin decomposition, but we will have a shortcut which actually is better because it's generalizable to a context when we don't understand so well the thick thin decomposition. But the thick thin decomposition gives us a great understanding of the structure of a negatively curved or symmetric space, locally symmetric space of rank 1. So let's say for some application it will be enough to assume that, but mostly today we will assume that the curvature is between is strictly smaller than 0.
0 minus?
A is purely imaginary.
The curvature is strictly smaller than 0. Let's say from -1 to -1/4, that's the case of symmetric space of rank 1. So in symmetric space, this corresponds to symmetric space of rank 1. But all what I'm saying today will apply to this more general context. And last week we proved the Margulis lemma.
The curvature is constant or bounded?
Sorry?
Is the curvature constant or bounded?
The curvature is bounded between. It depends on the point and the direction that you choose. It's not a constant curvature. Even in rank 1, the only constant curvature means like real hyperbolic. Complex hyperbolic is already non-constant curvature. It depends on the direction that you look in the two directions that you look at in the tangent space. So the curvature in rank 1 it's bounded between minus quarter to -1. That's in general for rank 1. And recall the Margulis lemma. We will speak more about the Margulis lemma later, but we already proved a version of it, and the version is the following. So let's say let X be a Hadamard manifold. Dimension D, and with curvature, let's say with curvature K belongs to -1, 0, so you want to somehow bound the curvature, and the lemma says there is epsilon which depend on the dimension, such that if X is a point and gamma is a group generated by elements in gamma, a group of isometries generated by elements such that the displacement at X is less than epsilon, in his discrete group of isometry, generated by small element, then gamma is virtually nilpotent. So this is the version that we will use. Last week I gave a proof assuming that there is a Lie group acting transitively on X. This assumption is not needed for the lemma, but the proof, I like the proof with using the Haar measure and the compact stabilizer, so that's why I presented it. I think later I will present a proof which is more geometric and does not. We will present several proofs of the Margulis lemma, and sometimes we need more information that we can get in the case that there is a transitive group of isometries. Sometimes we will also assume that gamma is arithmetic, and then we'll get even more information. But for now, let's use this version. If you think about symmetric space, then we already proved this version. And so this is somehow the key lemma that allow us to understand the structure of the manifold when the injectivity radius is small. So let's discuss a bit isometries. So let now really assume that we are in negative, strictly negative, bounded negative curvature. So this A is, we don't care so much what is A. Epsilon and the constant will not depend on A. But we need some, we need it to be strictly negative. And so isometries of, or classification of isometries. So there are three types of isometries actually. So that's more general. So there are one is elliptic. So this corresponds to, there is a fixed point. If you want fix gamma is not empty. There are fixed points in X. There are fixed point, maybe one, maybe more, in the symmetric space, or in the Hadamard space. So that's elliptic. There is another type which we call the lexodromic or hyperbolic. Let's call it hyperbolic. And this corresponds to the fact that there is no fixed point, but the infimum of the displacement of gamma, this is a function on X. Recall that we denote by d gamma the function which gives you the distance between gamma x to x. So the infimum is attained in X. In that case, you can actually say what is the set, or if you want the infimum or the minimum, or if you want, you can say that min gamma, which is the set of X in X, such that d gamma of X equals the infimum of d gamma, is non-empty.
But we want it to be positive. No?
Yes, a non-empty, but fixed, but it's not elliptic. So yes, thank you. But a fixed gamma is empty. Yes, so it's not elliptic, but the minimum is attained. In the negatively curved case, this minimal set is just a line. It's a geodesic line. It's an axis on which the element gamma acts by translation, and rotate around it. So that's in the negatively curved case. In the higher rank case or non-positively curved case, this is a more complicated set. It could be like a two-dimensional plane, but it could be even worse. In general, we'll discuss it later. But in general, it's a set that you can decompose as a direct product of one line okay. Let's discuss the non-positive curve later, but it's more complicated, but it's still something we can say a thing about it, but it's not a one geodesic in general. These two family together are sometimes called semi-simple. And in the case that, in the Lie group case, in the case that we're looking at symmetric spaces, these are the elements, the matrices that correspond to them will be diagonalizable, will be semi-simple over the algebraic closure. So that's and the last type is parabolic, and this corresponds to the fact that mean gamma is empty. So, or if you want, the infimum of the gamma is not a stain. That's not stain.
And it can be zero?
What?
And it can be zero?
It's usually zero. Actually, in the case of negative curvature, it is zero. In general, it doesn't have to be zero. If it's zero, so sometimes it's called strictly parabolic. Gamma is strictly parabolic. If it's parabolic, then the infimum is zero. And if you want example of strictly parabolic element are unipotent element. If you think, for instance, if you think of the group SL2R acting on the real parabolic plane, then the element 1, 1, 1, 0. If you think about it, for instance, in the upper half space model, what it does, it takes this point I to the point I plus 1. It's actually Maple transformation, so it's translated along this Hor cycle, and the displacement here is positive. But if you go upper, you see that if you remember the metric, once we go up, we divide the metric by the altitude, so the infimum is zero. So unipotent has the displacement function, the infimum is zero. But in high rank, you can cook parabolic elements which are not strictly parabolic. So the infimum does not attain, but it's not zero. Okay, the classification of isometries. Let me not discuss it too much now in too many details, because we will do it later for the non-positively curved case, but also because in the midrasha 2 weeks from now Paul will prove this but let me just hint why this should be true. So I'll say hand waving. So you look at the visual compactification of the Hadamard space, and you get a compact ball. So what is the visual compactification? We discussed it in the midrasha several times. You look at all geodesic ray up to equivalence. Two rays are equivalent if they point to the same direction at infinity, or if you want, if the distance between them is bounded. So you look at all the rays, if you want, coming from a given point, all the rays, or you don't need them to come from a given point, but if you start from a given point, there is one ray, but this gives you a compactification of the Hadamard space, and you get a compact ball. If the space is n-dimensioned, you get a compact ball of dimension n. The boundary is a sphere of dimension 1 less. And every isometry here acts on this space by homeomorphism. There's no metric on the boundary. There are metrics, but not that does not respect this topology. So there's no natural metric on this compactification, but there is a topology, and the isometry group acts by homeomorphism. So by Brouwer fixed point theorem, any isometry has a fixed point. If the fixed point is inside, then it's elliptic. If it's not inside, then it's outside. And then you ask if there is another one. So if there is another one, so at least in the case that the curvature is strictly negative, there is a geodesic between any 2 points on the boundary. Manifold that has this property are called visibility manifold, and strictly negative curvature manifolds are visibility manifold. Will you prove this in your?
No. I'm not sure, but if you want me to prove it, I can.
Okay, let's discuss it. But that's a property of strictly negative curvature, and it's not true in say in higher rank. So there is a unique geodesic between every 2 points. So if you fix this and you fix this, and it's isometry that fix both must preserve the geodesic. And if it's preserved the geodesic, it acts by translation on the geodesic, and everywhere else it must act. The displacement is strictly bigger everywhere else, and so that's the hyperbolic case. And if there is only one fixed point at infinity, then you can show that the infimum cannot attain, then does not attain, and it's a parabolic case. So since we're going to discuss it, I will not spend time on it here. Maybe we'll come back to it in the more general case when we discuss the non-positive curve.
So you want the group of isometries to be connected also?
Sorry?
So looking at the group of isometries or any isometry?
Any isometry. There's no usually the group of isometry is discrete. If the space is not homogeneous, there's no reason for it to be non-discrete. So that's the type of isometries. You know it also for thank you. So okay, so now let me discuss the Stickton decomposition, or maybe I will say one more thing about the isometries before we do that. So let's discuss a bit the function d gamma. So some facts about isometry. So beside this classification, so first d gamma is convex. So d gamma is a function. D gamma is a function from the space to the non-negative numbers, and why is it convex? Because the metric is non-positive curvature, and I mentioned in the first lecture that non-positive curvature is equivalent to the fact that the distance between any two geodesics is a convex function. So if you look, if you restrict d gamma to a geodesic, it's like looking at one geodesic c of t and another geodesic is gamma c of t. The distance between them is convex function, But that's exactly the meaning of saying that d gamma is a convex function. When you restrict it to a geodesic, it's a convex function. And in particular, if you look at the set d gamma less than equal than something, or let's say strictly less than a given number, so this is a convex set. It could be empty with smooth boundary. So if you want the normal, the external normal to the boundary, it's exactly the gradient of this function. This function is differentiable. The manifold we're discussing are at least the metric is at least C2 because they have curvature. Usually, when we discuss a non-positive curvature, in general, we will assume even that the metric is analytic, but in most cases, we don't need this assumption. So this is you should imagine some convex set with smooth boundary. This is where the displacement is less than a given number. For instance, if you are hyperbolic, then you have some axis and it will be a neighborhood of this axis. And if you are parabolic, it will be, if you want, a neighborhood of the fixed point at infinity. So it will be unbounded sets in these cases, but convex with smooth boundaries. Another thing is that in non-positive curvature, you have projections convex sets. So it's a fact, is another fact, if A inside X is convex, here I don't need to be with smooth boundary, any convex set, there is the nearest point projection pi A from X to A is well defined. So for any point in X, there is a unique point in A which minimizes the distance. If you never see it, then look at it as an exercise. It follows, for instance, from the cut zero property or from uniform convexity of the metric. So there is a well-defined map, and another property of it is that it's one Lifshitz, or it shrinks distances. So the distance between X to Y is always at least the distance between pi A of X, pi A of Y. So that's you should imagine I have a set A, and I have a point X, and the orthogonal the nearest point projection is come vertically to X if there is, anyway, if the boundary is smooth. If you have another point Y, then the distance must shrink. And okay, this is an exercise as well. This convex set, for instance, could be when we discussed the classification of isometries, I said if gamma is two fixed points in the boundary, then it has an axis which is invariant. An axis is a convex set. So you can look at the projection. So this is an axis C, is a geodesic, is an axis of hyperbolic isometry gamma. And if this is X, and this will be pi C of X, and somewhere here we have Y, or you have gamma X, and here we will have pi of gamma X, which is the same as gamma pi of X, because the projection is canonic and the isometry preserves the set. you see that the distance between x to gamma x is at least this. But if it was equal, then we could deduce that these two geodesic are parallel, they're equidistant, and then there is a lemma that we will discuss at the midrasha at some point called the flat strip theorem. That if you have two geodesic which are of constant distance, then the convex hull of them is a flat strip, is like a strip inside a Euclidean plane. So if you want, they live inside Euclidean plane.
Why is pi gamma? Gamma is pi?
This is in general if you have a convex set and suppose that an isometry preserves this set. Yes? So the isometry will commute with the projection to the set. Because the projection is canonic and the set is gamma invariant. I mean, by definition, we take it to the nearest point. The nearest point
to gamma inverse.
Yeah, the nearest point to if this is the nearest point to x, and this is gamma x, then this is the nearest point to gamma x. It must be gamma of the nearest point to x. So that's by the definition of nearest point projection. It's metrically defined, so it must commute with the isometry that preserves the set. What else do I need to tell you about isometry before I start with the proof? Maybe that's all. Yeah, there is a lemma. Okay, let's suppose now that we are in strict negative curvature, and then here is the lemma. If let's say gamma, if alpha and beta are commuting isometries, then what do I need? I need the following first. The sub-level set sets of alpha are beta invariant. So this means that if I look at the set d alpha less than t, this is a sublevel set. So I said that this is a convex set with smooth boundary, so it will be beta invariant. And the second thing I want to say is that alpha and beta has the same type. So okay, I don't want to involve elliptic, so let's say if alpha is hyperbolic, suppose that if alpha and beta are not elliptic, suppose both are not elliptic. So if they are not elliptic, they are either hyperbolic or parabolic. Then they are simultaneously hyperbolic or parabolic and with the same axis or the same fixed point between. Then if alpha is hyperbolic, then so is beta, and they share the same axis. They have the same axis. And if alpha is parabolic, then of course, beta must be, because if we believe this, then beta is also, then so is beta, and they have the same fixed point at infinity, the boundary. So that's this is somehow where I don't want to involve elliptics. So you can also say something about if one of them is elliptic, but the 16 decomposition is about manifold, and the fundamental group of manifold are group with no elliptics, and you can start to prove something for orbifold, but then you will see that it's getting more dirty, so it's not as nice.
This is not true in the general non-positive curve?
What?
The lemma.
This lemma is true in this lemma is true in general. If two elements commute, if one of them is parabolic, okay, not precisely, right? You can have okay, just let me give you a stupid example. Think of the group SL2R was SL2R, which act by isometries on H2 was H2. And now take two isometries. One of them acts trivially here and parabolic here. The other acts trivially here and hyperbolic here. So they commute, but they are not at the same time.
And this is not bounded negatively curved?
Yeah, this is bounded. The curvature is between 0 and -1. So this is a. So
But it can be zero. Okay, yeah.
you can say thing in non-positive curvature, but it's hard. I mean, there are more. You have to consider more. Okay. The 16 decomposition is special to rank 1 or to negative curvature, and it's also special to manifold. So I now we will speak about. We already assumed that. Now we will assume that M is a manifold. So let M x1 gamma be a X manifold. It's manifold locally isometric to X. So it means that gamma, in particular, gamma acts on X discretely and freely. Freely it means that there are no fixed point of non-trivial elements, so no elliptic elements. And so we fix X, there is some epsilon which depends on the dimension, the Margulis constant. And now, if you remember, we denoted by M less than epsilon the thin part, the point of all X in M, such that the injectivity radius at X is less than epsilon. And we want to understand the shape of that set. So let let M less than epsilon tilde in X be the pre-image of M less than epsilon in X. X is the universal cover of M, and we can pull back this thin part, this thin part. And furthermore, let than epsilon tilde 0 be a connected component. A connected component of this. So this may be it usually will not be connected, and now I take a connected component. And I want to understand, as you may think, even this set is not connected, but if I take a connected component of it, its pre-image is also not connected, but I take a connected component of it, and it will be enough to understand that, because this will project onto the connected component here. So let's say what I mean. So first, what is m tilde less than epsilon? I can say exactly what it is. It's the union over all gamma in gamma, which are not the identity, of the displacement of gamma is less than 2 epsilon. 2 epsilon? Or epsilon over 2 or 2 epsilon? Let's see, if I have in the manifold, if the injectivity radius is epsilon, it means that it means that this loop is at least 2 epsilon. So yeah, that's okay. Right? If I look at if the distance between x, to gamma x is less than epsilon, then if I look at the loop that corresponds to gamma, starting from x, I can make it of length less than 2 epsilon, and this means that the ball of radius epsilon around x cannot be injected, because it cannot be, if I have a point x and the epsilon ball here is injected, then any non-trivial loop must leave the ball and then come back to the ball. So it does, the length it does inside the ball is at least 2 epsilon. So any non-trivial loop is at least 2 epsilon, and this means that. Yeah. Do you agree with that or no? Okay. Maybe try to meditate on it a bit yourself.
You mean intersection?
What? The union. Any element in gamma correspond to some loop in the fundamental, some non-trivial loop in the fundamental loop.
Right. Yeah, it's not the thing.
The thing. But look, it's set of the type that we like. It's a union of convex set with smooth boundaries. It's something that we can handle. Each of these set is a union of convex set with smooth boundaries. And if I take a connected component here, then it will be a union over, let's say, gamma 0, where this is a subset of gamma. It's not a subgroup, it's a subset of the same set. D gamma less than 2 epsilon.
Each of these is
Gamma 0 inside gamma is a subset. Some subset. And one remark that to think about, this set is what Ballman-Gomer-Schroeder called gamma precisely invariant. What do I mean by that? Any element in gamma does not have to preserve this, but if it does not, it either take it to a set which is disjoint or to the same. So m less than epsilon tilde 0 is gamma precisely invariant, which means, i.e., gamma, every gamma, for any gamma, either either gamma equals the set equals, or gamma take is to something which is completely disjoint. Okay?
Why do you have gamma zero?
What?
Why is each of these connected?
Sorry?
Why do you know that there's such a gamma zero? That M.
Okay. Let's. This is obvious. So I look at I have a union. If I look at M less than epsilon tilde, what is it? Is d gamma 1 less than epsilon, d gamma 2 less than epsilon, d gamma 3 less than epsilon. I have a union of convex set, gamma 4 less than epsilon. I have a union of convex set with smooth boundary. And now I take some connected component of it. So I look at a connected component correspond to a subset. I look at all the I pick this, and if I look at everyone that intersect it, let's d gamma 5 less than epsilon, and so on. So I take one connected component.
Why is that dependent that they have smooth boundary?
What? I didn't prove this.
No, but does it matter for what you said?
No. No. The fact that I keep saying that they have smooth boundary because a month later I will use it. In the future I will use the fact that in the future I will need to understand the boundary. But now I don't care. I just convex sets. The sub-level sets are convex sets. They're nice set. We will actually, if there will be time, we'll do some exercise and try to see what they are in an hyperbolic case. In three-dimensional hyperbolic case, these sets are extremely nice, each of them. The union is not so nice, but each of them is extremely nice. So I would like to show you that because then you will have some clue why the thin part is more complicated than one may think. Because even the hyperbolic case, it's okay. But let's proceed now, and we try to understand this connected component. So here is what I claim. So we have this m less than epsilon tilde, and we have gamma 0, which is a subset of gamma. We will actually see that it's actually okay. Let's see what it is. So this is a union of gamma I subset, and pick gamma 0 inside this set. So then it has two options. Either it's hyperbolic or parabolic, because we don't consider elliptic. So I claim the following. If gamma 0 is hyperbolic, then gamma, all this consists of hyperbolic elements with the same axis, with a common axis, and gamma 0 is not a group. Actually, gamma 0 will be a finite set. So far we don't know it, but we will see that it's a finite set. But this, the group generated is a cyclic group. So that's what, if one of them is hyperbolic, then this, and if you remember the fixed in decomposition, this will correspond to the fact, this will imply that m less than epsilon 0 will be m less than epsilon tilde 0 divided by the group gamma 0, group generated at gamma 0, and this will be is a tube, a tubular neighborhood of a short geodesic. And the geodesic will be the projection of this common axis, and this will be some neighborhood. So a priori we start with something complicated, but we'll see that we get if the two-dimensional picture is like that. You have some short geodesic and some neighborhood. This will be the final thin component.
We don't denote the connected component with respect to gamma 0,
I started with a connected component.
but it was defined by gamma 0, by gamma connected.
Gamma 0 is defined by.
Like there can be different connected components. Some are cyclic, some not cyclic.
No.
Gamma 0
Yes.
isn't a connected component of gamma.
Hmm?
Gamma 0 is just some subset.
Right, but m tilde 0 can be, gamma 0 can be or cyclic or not a cyclic, right?
No, gamma 0 is a set.
Right,
But it's-
the group
The
generator.
group, it will be cyclic. If it has a hyperbolic element, it will be
Right.
cyclic.
So we have different kinds of connected sets in the universal group. So that's
Yeah.
ones which have the group is cyclic and ones which.
No, all of them will be.
So it doesn't matter which connected
No,
component I choose.
no. You will get, if you take another connected component, you will get another cyclic group which is actually conjugated to the same one.
But
Even if they are not
but then
hyperbolic.
once we have
What?
Even if they are not.
No. Now I discuss the hyperbolic case.
Okay.
but then once we have one hyperbolic element, we can just look at the connected component of this, and everything will be cyclic.
Wait.
If we have one hyperbolic element,
In gamma, in the
In
B
gamma.
group,
yeah. So just look at the connected d gamma from there and take
Ma-
its connected component.
Maybe it does not fit its connected component.
wait,
Or the thin
i-
part.
Of the thin, okay, of the thin part. Okay.
You said something is finite, not the group.
yeah, the set gamma 0 is finite. I didn't prove it yet. And it's true only in the
Like
case
usually,
hyperbolic.
right? But
no,
not
what?
necessarily. It's not necessarily.
It's not necessarily. In the parabolic case, it will be infinite.
Ah.
But in the hyperbolic case, it's finite. You will see why. I mean, later we'll see examples. So, but let me prove it. But this is claim 1, and claim 2. Okay. Let's put that. So so we have this picture, and suppose alpha and beta both belong to gamma 0. Or if you want, you see that
You're proving the claim now?
a proven claim. We know that this is a union. Okay, suppose that alpha and beta are in gamma 0. Or let's suppose. Okay. Let's suppose that gamma is in gamma 0. Okay. we want to show then there is a gamma 1, gamma 2, gamma n, a sequence in gamma 0 such that d gamma I less than epsilon intersect non-trivially d gamma I plus 1 less than epsilon, and gamma n equals gamma, right? You can move from this. Okay. Hence, to prove the claim, it is enough to show it is thus enough to show, let's prove this claim and then go to a break, that d gamma 1 less than epsilon intersect d gamma 2 less than epsilon implies that gamma 1 and gamma 2 are of the same type. So let me actually prove two claims. This is the claim, the same, more or less the same argument we will do for the parabolic case.
There's the intersection is non-empty.
Yeah, if the intersection is non-empty, thank you. So let me have a claim for hyperbolic and claim for parabolic. So after we prove this, so more or less at the same time, we prove the second claim that if gamma 0 is parabolic, then the group consists of parabolic with a common fixed point at infinity. So they share a parabolic element as a unique fixed point, and this will be the same unique fixed point to all of them.
But it need not be cyclic.
No, it won't be cyclic in general.
But also, to get the common axis, you need them to
To actually commute.
Wait. So now I say that two elements of the same type, or let's say alpha and beta, are of the same type. If this is a local definition, just for the proof, if they are either one hyperbolic with a common axis, or parabolic with a common fixed point at infinity. Okay. So now we assume we're in this case, and in order to prove both the blue and the red claim, I need to show you that it's enough to show that gamma 1 and gamma 2 are of the same type. So now we use the Margulis lemma, and then let's postpone by a few minutes the break. So the group gamma 1, gamma 2 by the Margulis lemma the group is virtually nilpotent.
So here you use the epsilon from the Margulis.
Yeah, actually I need to use half of
Half
it
of
because
it, yes.
I need to use half of the Margulis constant. So our epsilon is half of the Margulis constant, and you see that if you have a point in the intersection, the displacement of each of them is less than epsilon. Yeah, everywhere I should write 2 epsilon, but let's ignore that. So by the Margulis lemma, it's virtually nilpotent. So there are n and m, or if you want, so let n inside group gamma 1, gamma 2 be nilpotent, normal, or finite index. And let, if you want, gamma in N be a non-trivial central element. So in an important group, you have a center, non-trivial center. So, and of finite index, let the index be N. So, look at the sequence, consider gamma 1, gamma 1 to the n, gamma 2 to the n, gamma 2. This is a sequence of length 5.
Tsachik, why does n have, like, it's virtually nilpotent, so we have a subgroup of finite index. Why does this subgroup have to be normal?
This is a general lemma in group theory. If you have a finitely generated group, or not even finitely generated, if you have a group, and you have a group of finite index, then it has only finitely many conjugates, right? Because if the index is 10, there are only at most 10 conjugates of the group. Intersect all of them, you get a normal group, normal subgroup. And it's still a finite index because the index is sub multiplicative.
So when we say virtually, we can always look at the normal.
Yeah, if you have you can always look at it. So this is a general fact. So when you in many applications you would prefer to take the normal subgroup. The subgroup, the polynomial subgroup could be normal. Sometimes you don't want to pay the price of going to larger index when you want precise constant, but sometimes in proving a qualitative statement, you can assume that it's normal. And then you have this sequence. What's special about this sequence? Each person commute with the next one. Gamma 1 commute with gamma 1 to the n. Gamma 1 to the n is inside the normal subgroup, and gamma is central there, so it commute. Same reason this commute and this commute. So,
Wait. So as we virtually nilpotent, I mean, you didn't assume anything about it, but we just assume it's finitely generated and virtually nilpotent.
it's 2 generated.
Yeah, but we can work with 3 elements.
What?
Why can't it work with 3 elements?
No. What? I just proved that if you have 2 elements, then they are of the same type. If you have 2 elements whose sum-level sets intersect, then they are of the same type. We agree that it's enough to prove that. And then you can move from one to the next, to the next, to the next. All of them will be of the same type, which means all of them are hyperbolic with the same axis, or all of them parabolic with the same fixed point of view. Okay? So now we are just here and here. By this intersection, they generate a virtually important group, and we have this 5-step sequence.
Like pairwise.
What?
Like pairwise.
Pairwise
No.
commute.
No, not even pairwise.
Not pairwise.
This
Each commutes with the next.
Yeah,
Step
each commute with the
commutes.
next. Each commute with the next. I don't know that gamma 1 commute with gamma 2. We will know it in the hyperbolic case soon, but we don't know it in the yet, and it's not generally true in the parabolic case. But now, from the lemma we had before, did we have this lemma?
Yeah.
That if 2 elements commute, if one of them is a parabolic, then
I think you proved it, but
what?
you wrote it, you didn't prove it.
I didn't prove it. Why didn't I prove it? I thought I proved it, but okay. By the lemma, let me prove it hand waving. Suppose that one of them is hyperbolic. If another element commute with it, then it preserves the axis. The axis is a convex set. If something preserve a convex set, it's attained its minimum or its infimum on the convex set. So the second element must attain the minimum on the axis. But on the axis, what are the isometry of the axis of a line? Just translation. So you see. So if the first element preserve a line, the second element must preserve also the line, and therefore it's hyperbolic. So this is the proof. I should have given a formal proof, but I think this is a proof of this lemma that I'm using now. All of them are simultaneously of the same type. This is hyperbolic, this one is the same with the same axis and so on. This is parabolic. Okay. So we are almost done with this. Now we need to split between the.
Why is gamma? What shows me that gamma 1 to the n is not 1, is not trivial, it's parabolic.
So it's torsional free,
Yeah, that's that's a great question. Somehow I skipped it. I owe you a proof of it, but lemma or proposition, let's call it. I will say the proof, you will see it. If gamma act on X freely and discretely, then gamma is torsion free. So there are no non-trivial elements of finite order. And why is that? Suppose you have an element of finite order, look at its orbit. Pick some point and look at the orbit. It's a finite set, which is invariant under the element. This finite set has a center, circumcenter, or something called Chebyshev center, a unique point which minimize where's the what? And this will be a fixed point.
So in the parabolic case, so we can have.
No. I say if there is torsion, there are fixed points. Okay. Torsion element must be elliptic. That's what I say. In the Lie group case, you know that the stabilizer of each point is compact. So you don't need the Lie group. Okay, so we are in the. I didn't find a right place to do the break. So we're really close to the end of this fixing the composition. So should we have a 5-minute break now, or should I finish the proof? Let's finish the proof. So now split the two cases. Suppose now first that this gamma 0 consists of hyperbolic with common axis. So imagine you have an axis and you have this some point x, and you have gamma 1x, gamma 2x, and so this group gamma 0, let's call the axis C. Gamma 0 also preserve this geodesic. So pick an element gamma in this group gamma 0 with minimal displacement or minimal translation length actually generate gamma 0. Do you see that? If you take the element with minimal displacement length, it must generate everything. Because
Yes, but why is the minimum thing?
this is a why is the minimum? We assume that gamma is discrete. Gamma acts discretely.
Okay, right.
Yeah, gamma acts discretely properly. So the minimum we take, and now you have x, you have gamma x, gamma square x, and why it generate everything? Because suppose we have somewhere here gamma 1x.
But this gamma is not the same as your central.
No, it's not the same. Let's call it maybe I should call it alpha. So alpha then. But then, okay. My writing is so bad, so I don't need it to fix it. Gamma is the same. So alpha to the n x, and it will get near any other point, and if it's get near, it must hit it, because otherwise you get something of smaller displacement. And if you hit it, then so any element, so you will get at gamma 1, if you want, times alpha to the minus n fix x. But if it fix x, then it must, since there are no torsion, it means that alpha to the n equals gamma. So by this you see that every element is a power of this gamma, so it's generated. And you see, I said that this set gamma 0 is finite. It's finite because gamma 0 had only element with displacement less than epsilon. At some point the displacement here will be bigger than epsilon, and this is the line of minimal displacement, so it will be bigger than epsilon everywhere, so this sublevel set will be empty. So this is the hyperbolic case. The parabolic case is very similar. You will get in that case, in the parabolic case, in the remaining case, gamma 0 is a parabolic sub, if you want, parabolic group. Okay, parabolic group is a term usually used for Lie groups, but you mean it's a parabolic subgroup of gamma, so it consists of parabolic elements that fix the same point at infinity. And at that point, I don't want to say anything more about it. So I don't know it's cyclic. I don't know so much about it, but but you will know something about m less than epsilon. About this is the union over all gamma 0 of d gamma less than epsilon. So these are, if you want, are all neighborhood of the same point at infinity, or if you want to, each of them is like a neighborhood of a point at infinity, and at this set I don't want to say much about it, but also so far we didn't use the fact that M has finite volume. So now we use it. If M has finite volume, then M less than epsilon 0, the connected component, which will be M less than epsilon tilde 0 divided by this group, will have finite volume, have finite volume. As well. Now, I claim that in this case, there is a common fixed point at infinity, and if you any point in this set will, the ray that goes to this set, to this point, is inside a set. So all of them will be like, if you want, a monotonic neighborhood of that point. Because the displacement goes to zero monotonically when you go here. Okay, there are some facts I didn't prove. Let's do a break now, and after the break I will reformulate the statement of the sixth decomposition, and we discuss it a bit further. And yeah.